Okay, this is a bonus video, and it's going to be a short introduction to nonlinear related or nonlinear correlated variables. The idea is very simple. We are going to have two random variables, which are basically not independent. On the other hand, when you apply the correlation measure on them, the correlation is going to be equal to 0. Therefore, we are going to simply say that the correlation does not necessarily entail independence. On the other hand, as I said previously, independence entails zero correlation. Well, actually, usually we are going to have symmetric. We may have symmetric functions which are with symmetric functions of two variables, which are actually not independent, but on the other hand, they are going to come out to be correlation. Let's see, I'll try to handle this ruler, but I couldn't do it, so I'm going to get rid of that. All right, just a typical our poor XYZ axis. Let's say that this is our X and Y are two random variables, and let's say we have, I'm going to first talk about a discrete case, +1. We have non-zero probability mass function at these four values only. As you can see, that's a very simple probability mass function, or a function of two random variables. Nothing fancy here. So here, let's give equal weight to each of these points. So this is our probability mass function for X and Y. They are defined in non-zero probabilities at 4 points. Now you can easily show that. I'm going to skip that part. Expected value of X is equal to 0. Expected value of Y is equal to 0. Actually, you can easily see that the center of mass of this system is at 0, 0 point. So in vectorial form, you can show it as 0, 0 if you like. Anyway, now we have to find, in order to find the covariance between X and Y, so that we are going to find the correlation, we have to find the double integral of xy multiplied by the joint probability mass function, right? Summation over X and Y, then subtracted from mu X, mu Y, the expected values. Note that since these are equal to 0, this is going to be simply equal to 0. So we only have to consider this part. So to consider this part is going to be very easy. X times Y times the probability mass function. Note that probability mass function is always in 4 different places, all 0.5, 0.25. So it's going to be 1 over 4 in common parentheses. And since we have 4 points with non-zero values, non-zero probability values, I'm just going to write them. So for instance, starting from this one, X is +1. And the Y value here, corresponding value is 0. Plus, let's talk about this one. Y is -1, but X is 0. And this one is going to be equal to plus -1 times Y is 0 plus the last point is going to be X is 0 plus 1. So as you can see, we have all zeros here. This is going to be equal to simply 0. Basically, correlation of X and Y is going to be equal to covariance of X and Y, which is equal to 0 divided by the variance of standard deviation of X and standard deviation of Y. And I don't need to calculate them. Since this is equal to 0, this is equal to 0. On the other hand, X and Y are not independent. And how can we prove that? Actually, we can prove that X and Y are not independent. Or let's say proof of. You have to, if you recall, we had 4 different conditions. Actually, we can use the first 3, any first 3, to show that these are not independent. And I'm going to use my favorite. It's going to be the conditional probability mass function of X, and given some Y value for any X value should be equal to marginal probability mass function of X for independent X and Y. If this condition is satisfied, that for all X and Y points, for all X and Y values, then we can say that X and Y are independent. Actually, I should have written this here. X and Y are independent. Let's check this for a single point. It may be any point, it doesn't matter. Let's, for instance, consider this one. So first, let me find the marginal probability mass function that X is equal to 1. This is basically going to be equal to fxy 1y summed over all y values. Note that I just follow the basics. This is the definition of the marginal probability mass function. So this is going to be equal to, we have at 1, we have only when y is equal to 0, we have a non-zero probability. For other values, there is no other y value when x is equal to 1. Therefore, this is going to be equal to fxy 1, 0, which is going to be equal to 0.25. That's great. In the frame. Now let's continue with this part. We are going to also calculate this part, fxy given some value. Let this value be equal to 1, let's say, for x is equal to 1. What is this equal to? Note that when y is equal to 1 here, there is no way x is going to take the value of 1 here, because when y is equal to 1, the only non-zero value, so let me put it that way, when y is equal to 1, then the conditional probability that x is going to be equal to 0 is going to be equal to probability of xy, x is equal to 0, y is equal to 1, divided by probability of y is equal to 1. All right. So this probability is going to be equal to fxy is equal to 0 and 1. Let's see what's that equal to. That's going to be equal to 0.25. And if y is equal to 1 is going to be simply a summation. Again, it's going to be a summation of x, y, x1 over all x values of 1. Please pay attention to what I'm doing. I never shift to practical approaches, so-called heuristic approaches. I just follow always the rules. And this is going to be equal to, since there is only one element here where it's going to be equal to 0, this is going to be equal to 0, 1, therefore it's going to be equal to 0.0.25, is equal to 1. So since this probability is equal to 1, it means that this probability is equal to 0, because this exhausts all the probability value, because probability can at most equal to 1. So when y is equal to 1, well, since x is equal to 0 as 1 probability, then being x equal to 1 is 0 probability. So this actually finishes the proof. You should see that these two are not equal to each other. On the other hand, for independent x and y, you have to satisfy this condition. Therefore, x and y are not independent. So here is all things. Although x are not independent, their correlation and also covariance are equal to 0. That's actually the moral of the story. All right, the second question I would like to solve is a continuous one. Let's take a circular region, x and y again, sorry. And this is going to be our circle. And let's say that, all right, this doesn't look very nice, but do your best to understand what this shape looks like. Actually, this looks like a cylinder, right? So this is going to be our fxy. So basically between plus r and minus r, which correspond to radius, plus r and minus r, we have this circle here. So the interior region of this circle is accessible, and over this interior region of the circle, we have uniform probability density. Therefore, actually now, if we call this value where actually the height of the cylinder C, then we can find the volume of this cylinder is going to be equal to, so it's going to be fxy, xy dx dy, and this is going to be a constant, and this is over the domain of x, and y is going to be equal to 1. I don't need to integrate. It's very simple because this is a cylinder, so it's going to be the PR square is this area multiplied by c is equal to 1, so therefore c is going to be equal to 1 over PR square. So therefore our probability density function is going to be equal to, for this two random variables, is going to be equal to PR square constant. On the other hand, we should also write the condition that x square plus y square is smaller equal r square. So this is the domain of x and y, and this is actually the probability, corresponding probability density function. Now, when you see this, you can actually you should instantly recall the idea that since the domain of x and y does not form a rectangle, therefore x and y are not independent. But let's, well, this is very much obvious, but let's go with the correlation and let's see what's going on. So in order to find the correlation and covariance, we have to find covariance xy, which is x times y f xy dx dy minus mu x mu y. Now, without proof, and well, you can do it, it's going to be very easily. You can easily see that the center of mass of this system, since it's uniform distributed, is going to be 0, 0. Therefore, the whole thing is going to be equal to 0. But so for those who are curious, just prove it yourself. So this is going to be only the covariance part is going to relate with this part. All right, now let's do it. Let's put the integral x times y. Instead of xy, I'm going to write 1 pi over r squared, so I can write it easily here since it's a constant. Then I'm going to put dy and dx. Let's handle dx is going to be from minus r to r. So it's going to be this, for instance, we are going to go from actually minus r to r. We are anywhere here. So we are, let's say, at this point. When we are at this point, integration will be, note that between this point here, from this y value, from this y value. And the corresponding y values, therefore, is going to be equal to r square minus x square in square root plus, again in square root, r square minus x square. So we are going to, well, actually, we can even take this x here to make it seem maybe nicer. So we are going to be concentrating on this integral. So this is going to be y square over 2, right, with r square minus x square with minus r square minus x square. Let's get rid of this also 2 here, put 2 here, it's going to be here. So we are going to have, instead of this one, it's going to be r square minus x square. When you put this whole thing instead of y square, this negative sign will turn into positive, and this is going to be minus r square plus x square. And these will cancel, and we got 0 here. Therefore, even in the inner integration, we got 0 here, so the integral is going to be equal to 0. So hence, covariance is going to be equal to 0. Correlation of x and y are also going to be equal to 0. On the other hand, as I said previously, x and y are not independent. That's not an if and then statement. So, though x and y are not independent, their correlation is equal to 0. Note that this is linear correlation. They are non-linearly related. And as I said, one example or one typical case of non-linear relation are symmetric relations. And actually, as you can see, there is a symmetric relation here. And for these cases, relying on only on Pearson correlation coefficient may be misleading.